energies, these are the primary emitters in the sky. Okay, so they're quite impressive that way. Also, they're impressive because of their huge luminosities, as we will see. So let's start from the very beginning, and and I'll tell you a little bit of the history, because I think without history, it's very difficult to make sense of how far we've come. So it started as a study in itself in 1943. And this astronomer by the name of Carl Seifert was one of the few people who realized that there were a whole set of galaxies which were slightly different from other galaxies. And so the image, actually this is not picking up so well here, but maybe you can see. So these are actually two images, black and white images of two spiral galaxies which happen to be face on. And you see the dust lanes, you see some kind of spiral arms. But in this particular galaxy, you also see the cross, right? Which is like basically telling you there is a point source there. This is kind of the point spread function is being, So there is some bright thing in the center of this particular galaxy. And Carl Seifert realized that there was, maybe 1 in 100 spiral galaxies seem to be like this. The second thing which was very peculiar about these galaxies was that they were showing a lot of emission lines, which I'll show in the next slide. In their spectra, in their optical spectra, they were full of emission lines, whereas a normal galaxy is actually, the spectra is dominated by absorption lines. And those absorption lines are basically from the stars that make that galaxy. So something else above the stars is also emitting shows emission lines. Okay, but this was already actually observationally found out even earlier. So the first people who actually found this was in 1908. There was a PhD student called Edward Fath, whose PhD dissertation was to build a spectrograph. So when they made that spectrograph, they actually imaged some of these galaxies and already found some galaxies which had emission lines. But they didn't know what they were due to, and they thought maybe they were just like something peculiar, maybe some planetary nebulae, etc. So they just kept them, on the side. There was no attention paid to them. And then in 1917, already Slipher, he basically kind of confirmed whatever Edward Fath had seen. So they were also able to see those lines in much better signal to noise ratio. And even Edwin Hubble, whom I'm sure you all know, had also imaged some of these galaxies and found these emission lines. But again, for the longest time, it was not clear that they were actually a class of objects, and it was not clear what they were. So it was only Carl Seifert who kind of then, said, okay, there is a whole set of galaxies like this, and a systematic study kind of began. Okay, so this slide is basically showing you the spectra of a normal galaxy versus a Seifert galaxy. Now these galaxies are called Seifert galaxies after Carl Seifert. And a normal galaxy, so this is what I was saying, all these are absorption lines which are coming from the photospheres of the stars in the galaxy. But on the right side you see emission lines, very strong emission lines. The elements that are producing those lines are also given there: oxygen, helium-2, neon-5, silicon-4, whatever. So a lot of very high ionization emission lines are seen. Okay, so these were the two criteria which distinguish these kind of galaxies, now called Seifert galaxies: a point-like nucleus and emission line spectra. Now this luminosity, the interest came because the luminosity of that point source or the center of that galaxy could actually, in optical light, was equivalent to the starlight of the entire galaxy. So a normal galaxy contains around 100 billion stars, so 10 to the 11 stars, and the luminosity of this point source was equal to that. Okay, so already it's very, very, so it's a point source, which means it's unresolved at whatever telescopes you are observing with. So these will be ground-based optical observations, which will be at best less than 1 arcsecond. So it's kind of giving you already some sort of size from which this luminosity is being generated, which turns out to be around 100 parsecs. Okay, so 100 parsec has 10 to the 11 solar luminosity. So that's already very extreme. But still, it was this these galaxies didn't get as much attention until the beginning of radio astronomy. So after radio astronomy came about and radio interferometry became possible, that is where the interest came back to these objects. And the thing that happened to create interest was the discovery of quasars. Okay, so the discovery of quasars is quite an interesting story in astrophysics. I mean, if you there are whole articles on just this discovery because it is quite interesting how it happened. And so there were these two set of astronomers. One was these were radio astronomers in Australia. This is Hazan McKay Shimmons. This is 1963. So already 20 years have passed since the CIFR galaxies were found, and still there was not much attention given to them. So 20 years later, these radio astronomers are using the Parkes telescope, which is a very 200 kind of feet diameter telescope, single telescope, radio telescope in Australia. And what they did was they used a very clever technique called lunar occultation, by which they could get, even though the telescope itself didn't have enough resolution, it had a resolution of 14 arc minutes. Okay, I told you, like a normal optical telescope, even a small one, will have an arc second resolution. So this is 14 arc minutes. But in spite of this poor resolution, they could get actually very accurate positions of these objects in the sky because of this method of lunar occultation. So what they did, when they did that, they found that this particular radio source, 3C273, which is just the entry in the 3rd Cambridge catalogue, which is a radio survey. And they found that it was coinciding with what looked like a star, and a very bright star actually. It's a 13th magnitude star. So that is the image of that. Very, very bright star. You don't see any galaxy, you just see a star. And at the same time, in the US, Martin Schmidt actually, once the accurate position was obtained from the lunar occultation technique, obtained the spectrum of this 3C273 optical spectrum, and at Palomar, using the Palomar observatory, and was able to identify that the emission lines that they saw were actually the Balmer series of hydrogen, but at a high redshift. Actually, that was the highest redshift at that time. The redshift turned out to be 0.158. So I will show you the spectrum in the next slide. And there was a little bit of debate also whether this redshift is actually, is a quasar, for example. I mean, they're now called quasars. Was something that's kind of ejected from our own galaxy and is just moving away fast, so it has this very large redshift. But now we know that this is actually a cosmological redshift, and it's because of the expansion of the universe. So, okay, before I show the spectrum, these objects came to be called quasi-stellar objects because they look like stars, and since they also had radio images, and in the radio images also at that point they were still point sources, so they were called quasi-stellar radio sources, and that is how the word quasars came about. And so QSOs were kind of identified in optical surveys, and quasars were actually identified in radio surveys, but now we use these interchangeably. And the interest really came from the fact of this high redshift and greater luminosity. So they were actually even 100 times more luminous than CIFR galaxies. So now, not only do you have a more luminous source, it's also at a very high redshift. I mean, so the constraints, the energy constraints became much more severe, right? That is when the interest, finally, the astronomy community kind of got interested in this phenomenon. So let me first show you the slide, the redshift thing, and then we will talk more about that. So the spectrum of 3C273 is on the top panel, and the comparison spectrum in maybe terrestrial conditions would be at the bottom panel. So what Martin Schmidt found was that these lines of H beta, H gamma, H delta, they have a certain separation, and they have a certain change in their brightness, okay, which he was able to identify in the spectrum of 3C273, as you can see there. H beta, H gamma, delta. It's very, very faint. And so then he realized that these were just the Balmer series at a redshift of 0.158. And from the redshift, you can kind of get the distance to the source using these this relation. So this particular object was 787 megaparsec away. So very far away. That was the highest redshift at that point. Now with the JWST, for example, we know quasars at redshifts greater than 10. Okay, redshift greater than 10 means like the universe has just begun. It's like a few 100 million years old. So the age of the universe is like 13.6 billion years old, but the universe is just a few 100 million years old when the first quasars actually came, began to shine. So now, suddenly the interest of the community went into explaining these very, very luminous objects, and actually the 2020 Nobel Prize was awarded for this work to Roger Penrose and other astronomers who found the mass of the black hole in our own galaxy. Okay, and so that paper of Roger Penrose was written in 1965. So just 2 years after the discovery, there was a lot of theoretical work that went in to explain how can you get such high luminosities in such a compact region. And now we know it's because of the release of gravitational potential energy as matter falls onto supermassive black holes. This is how we understand now what this phenomenon is. And that was, of course, also suggested by Roger Penrose's. Roger Penrose's work was that GR predicts the existence of a singularity, so which is the supermassive black hole. Now we have much better radio telescopes. We are able to do much better radio imaging. We have much higher resolution, so you can now create very detailed images of these active galaxies. And so I want to show, of course, this beautiful image of a galaxy called, an active galaxy called Hercules A. So Hercules A, so here, again the yellow light that you see is actually optical light, which is what you would see in the sky. And there is this fuzz is an elliptical galaxy. And in fact, there is another smaller galaxy here also, which is kind of falling into this larger elliptical galaxy. And from the supermassive black hole in this galaxy, jets are being launched, and these jets are basically jets of plasma. The pink thing that you see is radio waves, which of course we can't see, but radio telescopes like GMRT can actually detect. And this pink emission is coming from synchrotron emission. So these are charged particles which are kind of ejected from these black hole accretion disk systems. The charged particle, we don't still know the content. They could be electron positrons, they could be electron protons. The composition of this plasma is not clear, but the fact that it is emitting synchrotron radiation is very clear. Okay, so these are charged particles moving in strong field, magnetic fields. Okay, so so this is an image, of course, which use the Webb Space Telescope as well as multiple resolutions of the very large array telescope and multiple frequencies as well. So now we can present this cartoon to show what we think is happening in an active galactic nucleus. And so the idea is that there is a supermassive black hole here, which is that black thing that's shown there. Then matter is kind of falling onto this black hole through an accretion disk. The accretion disk structure we still don't know. And of course it will depend on the accretion rate. The accretion rates decide the structure of the accretion disk. And there is some gas which is moving fast around this black hole, which is producing those emission lines that we saw in the previous slides. And so it's basically, some of those lines are very broad, which means they have Doppler widths of a few thousand kilometers per second. And so those are called broad lines. And they are basically being produced by this gas around the black hole. Then there is also gas far away, which is moving slower, and that is giving rise to the narrow lines. So in this slide, for example, this slide, a broad line would be something like this, there's a broad line here, and there's a narrow line on top. Okay, so the broad base of a line is just the velocity widths are few thousand kilometers per second, and so that is coming from this region very close to the black hole, and the narrow lines, which are few hundred kilometers per second, are coming from the gas further away. And then there are these jets, which are, of course, we saw them in the previous image, which are being launched from this black hole accretion system. What is not clear is how exactly they launched. So that is a lot of, it's an area of active research. And this orange-red thing is basically supposed to signify a lot of dust, which is kind of hiding your accretion disk and broadline clouds. And so it's in the shape of a torus, but we don't really know what the shape of this particular structure is. It's some obscuration. And that is kind of needed to explain why some Seyfert galaxies only show narrow lines in their spectra, and some show both broad and narrow lines. So this kind of a structure kind of explains all the observations so far that are known. So supermassive black hole is a black hole which has a mass of 1 million to 1 billion solar masses. So that's the definition of a supermassive black hole. A broadline region, I already told you, several thousand kilometers per second gas. Narrow lines, just a few hundred kilometers per second. They also, the electron densities of these gas clouds can also be inferred from the spectra. So you can look at the emission lines, you can do line ratios, you can see which lines are present, which are absent, and get limits on the electron density of the gas which is emitting those lines. So those have been obtained by the study of spectra. And so the broadline clouds, for example, are very dense clouds. They're moving fast, they're also very dense. The narrowline clouds are less dense, 10 to the 3 particles per cc, and they're moving slower. Okay, so all this information we have basically obtained from the spectroscopic observations, and some of it, of course, you can see, you can actually resolve the jets. Okay, so now I'll come to the one of the big open questions in AGN jet physics is, yeah, this doesn't look very nice. Actually, it looks nicer. Yeah, okay, anyway. There's a yellowish tinge, so some of this lobe emission is actually going missing. So but you can see, I think, hopefully that the radio galaxies, these are two images of radio galaxies, they're slightly different, right? So in this galaxy, you have a very narrow jet, whereas in this galaxy, you have a broad jet, and this broad jet is kind of opening up to give like a plume. In this particular galaxy, it's actually ending up in a hotspot. This is called a hotspot. And then there is some plasma behind it, behind the hotspot. So there are these two types of galaxies. And these have been named Fanaroff-Riley after the people who actually found this distinction. So FR2 type of jets and FR type 1 jets. What is interesting is that these two have a very different luminosity. These are the more powerful radioluminosity sources, these are less powerful. But there is a very sharp divide. So at 178 megahertz, the luminosity of these galaxies is greater than 10 to the 25 watts per hertz, and these are less than that. So the question is, why is it so sudden? So there have been suggestions that maybe there's some kind of a magnetic switch. Something happens which changes the jet from one particular morphology to the other. So somehow the jet immediately loses collimation. So this is a question which is open, and there's a lot of work being done to explain why these two jets are the way they are. Sometimes the spins of the black holes are invoked, and it's suggested that these galaxies probably have faster spinning black holes, the FR2s, versus slower spinning black holes in the FR1s. Okay, so these are the FR divide is a question which is still people are studying this question. Now there's another question, which is that this beautiful looking large sources, so the galaxy is right here, and you see the radio emission going very, very far. And this is basically the same galaxy at a higher resolution. So you can see the central part of that galaxy. You can see the jet as it just comes out of the black hole system. These kind of galaxies are actually rare. These beautiful large galaxies are actually rare. But what is more common are galaxies like this. So this is a nice spiral galaxy, but the radio emission is only here. So you see some very tiny jets, small radio jets. And this is actually the majority of the active galactic nuclei. 85% of active galactic nuclei are like that. Even though these are the most impressive ones, these are actually only 15% of AGN. So then the question is why? why do you have 15% of these active galaxies, why do you have such large jets versus 85% of them are small? So that's another open question, which is sometimes they call it the radio loud, radio quiet divide. Radio loud are sources which are, I mean, there is also a criterion people have given, but that's not so important. But basically, how does the radio flux density compare to the optical flux density of the AGN? If it's very large, then you have these large jets. When it's small, you have these small jets. So this radio loud, radio quiet divide is a question which also people are trying to answer. And again, people have suggested, so what happens often is that these radio quiet sources are in spiral galaxies, these are in elliptical galaxies. So one obvious difference is that spiral galaxies actually have less massive black holes. And in fact, it is suggested that elliptical galaxies form after mergers of several spiral galaxies. So their black holes are larger. And so maybe there is a explanation in these differences based on the black hole masses itself. Spins also could be important, of course. So these are areas of research which people who work on AGN jets are kind of involved in. Now, so we just talked about the radio so far, and in fact there is sometimes these AGN also show emission in optical light from jets. Okay, so sometimes they have optical jets as well. I don't know if you probably may have missed it because I didn't really stress on it, but if you look at this image of this quasar 3C273, you see the star very clearly, but you see that little line there, the white line thing there, that is actually a jet, which is from this galaxy, from this quasar, which is shining in optical light. So not just radio. You can see the jet in optical light in this particular quasar. So now, since we're talking about multi-wavelength aspects, I'm going to show this very interesting result. When the Chandra X-ray Observatory was launched, and the first time it opened its shutters, they had what is known as a calibrator source that they were trying to look to kind of focus their telescope actually. So a calibrator source is usually a point source. You want a source which has got a very simple structure or like, hardly any structure to be able to get the response of your telescope, right? You want a simple structure, otherwise then you don't know what is the complexity from. So they expected to see, it was a AGN called PKS, Parkes being the same telescope that I talked about, Ray telescope, and 0637-752. So the numbers are just the position of the source in the sky, and 0637 is telling you about the right ascension, and -75 is telling you about the declination. So where latitude, longitude in the celestial sphere. So so that's the Chandra X-ray Observatory. When they looked at this quasar, they expected to see a point source. And the expectation was that X-ray emission, actually X-ray emission is supposed to be very, very common. I mean, that is the expectation, and is also seen that because we have an accretion disk, you should have X-ray emission. And X-ray emission will come from this material which is kind of trying to fall onto the black hole. Because of viscosity, you should generate a lot of high energy photons. And so X-ray emission is kind of one of the signatures, expected signatures of an active galactic nucleus. But they expected a point source, but what they found was the point source is there, but there's also a jet. Okay, and so this was unexpected. And this jet is very large because this particular AGN is at a high redshift. So it's already at redshift of 0.654. So it's much higher than, for example, 3C273, which was when it was first discovered. And this is immediately a problem. So the problem is that if this is synchrotron emission, it should not be lasting this long. Because synchrotron emission, like any kind of emission, when you have more energetic particles, which will give rise to the high energy photons, they also decay faster. They can't have long lifetimes. So the expected lifetime actually, given some kind of magnetic field strength, which we assume, but we also derive from certain assumptions, and that the derived magnetic field is called the equipartition magnetic field, which we can discuss maybe if anybody is interested in the end. the lifetime in that kind of magnetic field strength for an X-ray emitting electron should be 10 years. Okay, but the jet is 100 kiloparsec. So 100,000 light years it has managed to stay. So that is a very, very intriguing question, and a lot of work is actually going on the study of these X-ray jets. Some of them are actually synchrotron emission, so somehow you have to keep these charged particles from losing energy. So you have to, even after they have actually left the black hole, you have to keep them energized to 100 kiloparsec scales. So that is another mystery. I mean, how will you keep them accelerated after they've left the black hole? Is it through magnetic reconnection events like you have, which you see on the sun? Could it be something else, some turbulence, something? So that's another big question in agent physics, is the existence, to explain the existence of these X-ray jets. And so here is a nice image of a much nicer looking jet, which is a radio galaxy close by called Picture A. And here the red emission is radio emission. It's a galaxy with a core and a jet and a hotspot, and all the blue emission that you see is X-rays. So there is a beautiful X-ray jet all the way till the hotspots. There is a lot of emission from the core itself. There is also diffuse X-ray emission coming from this AGN. Okay, so there is, it's quite exciting, and to explain all these different components is a lot of work. A lot of the diffuse emission that is coming is not from the same process which is giving you the X-ray jets. So normally you have to invoke inverse Compton scattering. So you have these, you already know that there is synchrotron emitting plasma, so you have charged particles which are moving relativistically. Then these relativistic charged particles can upscatter low energy photons to X-ray energies. So that's the inverse Compton process. And the low energy photons could be actually the cosmic microwave background photons. So CMB photons can be upscattered from these very fast charged particles to X-rays. So that's one way to explain these X-ray jets, is through the inverse Compton mechanism. But the rest of the diffuse emission could actually just be coming from bremsstrahlung. So all these different radiative mechanisms, you have to try to explain all the emission that you see from active galactic nuclei, and you need to kind of really get into the radiative physics to explain these. And still a lot of mysteries remain. So it's still not clear if this is actually inverse Compton. Maybe there is, I think now the consensus is that it's some kind of a mixture between synchrotron emission and inverse Compton emission. Now, let's come to this result, which is quite exciting. And this was the discovery of neutrinos from a blazar. So a blazar is kind of like a quasar, or there are other agents called BLAC objects. I mean, they're just different classes of the same phenomenon, where the jets of that particular agent are oriented towards you. So the object is in the sky in such a way that the jet is kind of pointing towards you. And because this jet is very fast, it's actually moving at speeds close to speed of light. So all kinds of strange effects happen. The emission becomes much more Doppler boosted, and the jet appears to be much faster than what it is actually in the rest-rim of the source. And this particular blazar may be actually emitting peta-electron volt neutrinos. Now, why is that exciting? And we'll talk about that. But I hope you, so this is a cartoon, of course, this is not the actual image, right? Because you don't have this kind of resolution. So this is the jet which is kind of coming towards us. That is the jet. And that is the IceCube observatory in the South Pole. And this is a cartoon to show what could be happening. So the exciting thing about this was that if you have neutrinos, it's telling you that maybe there are protons in the jets. Because to get neutrinos, you have to have a proton-photon interaction. And so that cartoon is kind of showing you, what could be happening with the proton and photon. You have all these, particles, including neutrinos. So that is quite exciting because now we're maybe getting a hint of what these jets are made of. So we know they're charged particles, we don't know the content. But when you have protons, then again it's a problem. Because protons are what, 1,000, how much heavier are they compared to electrons? It doesn't matter, I also don't remember. But something very large. When you have much more massive particles, then to get 100 kiloparsec scale jets, did I tell you Hercules? I forgot actually to tell you what the size of the jet in Hercules A. So Hercules A, that jet that we saw, is 500 kiloparsecs. Okay, 500,000 parsecs. And which is, if you want to get a sense of the distance, the typical distance between galaxies is 1 megaparsec. So it's half that distance between galaxies, so to get a sense of it. So if you now want to create such large jets with protons in them, then you need even, you know, mechanisms to generate, to keep them energized, which are even more extreme than what you need right now. So that is very exciting and also challenging at the same time. Okay, now another mystery comes about, because these large jets, even the first time they were actually discovered, there was a lot of theoretical work that went in to say how will you produce such large jets. And one of the, best way to produce these jets and keep them collimated is through this theoretical work by these astronomers by the name of Blanford and Znayak, who gave a model in 1977, and also they had another model in 1982, Blanford and Payne. So this, for short, it's called the BZ mechanism and BP mechanisms, where they basically suggested that because there is a spinning black hole, so fast spinning supermassive black hole, and there's an accretion disk which is also spinning, you can maybe extract electromagnetically the spin energy from this black hole. And because magnetic fields, of course, must be common there, and they must be threading the accretion disk and also the ergosphere of the black hole, maybe you can, with this fast rotation, you can extract energy from this rotating system. So that is Blanford-Znayak talks about extracting energy from the black hole itself. Blanford-Payne talks about extracting energy from the accretion disk. But in both the processes, what happens is here, so this is, let's say, the accretion disk, this is a cartoon, of course, and it's all threaded by magnetic fields. And then since everything is rotating, it creates this kind of a funnel. These are magnetic field lines. And this is a wave, it's a channel for the plasma to flow. And because of these magnetic field lines twisted, they actually act also to collimate. They actually collimate the plasma. They make sure that the jet stays collimated. So this is an idea which was put forth to explain these very large jets. Okay? But what is interesting is that after Event Horizon Telescope started functioning, and they have so far got the black hole shadows, which I will show in the next slide, of only 2 HEN. One of them is a galaxy called MET7, which is actually a very nice, very active galaxy, not far from us. And the second is our own Milky Way. Okay, so they have the black hole shadows of these two black holes. And so let's see that image. So these are the black hole shadows of MET7 and Sagittarius A star, which is the radio source in the center of our own galaxy. And here, in this image is slightly different. Of course, this should be black. It's looking pink, yellow. No, sorry, red. But this image is slightly different in the sense that this is showing magnetic fields. So this is a polarization image that has been acquired with the Event Horizon Telescope. So let me describe a little bit the Event Horizon Telescope. So this is using millimeter wave telescopes around the surface of the Earth, basically, including the ALMA observatory, which is a millimeter wave array in the Atacama Desert. And you are doing something called the Very Long Baseline Interferometry, VLBI. So VLBI is a way where you combine all these radio telescopes together to kind of work like a single telescope. So you get, you detect the wavefronts on all these different telescopes and you combine the signal so that this acts like a single telescope. So that is the whole idea of the aperture synthesis technique in radio astronomy, which is how the GMRT also works. It's just that the GMRT, you have the telescopes in kind of one location and you can actually get the signal from each of these through optical fibers. But if you have telescopes very far in different countries, you can't do that. So then you just record the data in those separate telescopes very accurately with some maser clocks, very accurate timestamps, and then you get them together in one place and correlate the signal. But because you have very high timing accuracy, you know exactly what time the wavefront reached that particular telescope, so you can do interferometry. So because you remember the resolution is lambda by d, so d you can of course with VLBI make very, very large. You can have telescopes at the almost opposite ends of the earth, or you can have telescopes on the ground and space. So that has been done as well. And then the other way to increase resolution is keep on going to smaller and smaller lambda. And that is what they did with millimeter wave telescopes. So you have the best possible resolution that you can get with the Event Horizon telescope, which is around 40 microarcsecond. So we've already gone from, we said optical telescopes, best is sub-arcsecond resolution. Then you went, you were talking about arcsecond scale resolution with radio interferometers like the very large array. Now you've gone to microarcsecond resolution. So that is what is needed to actually go all the way to the black hole. So this emission that you see, this ring structure, is synchrotron emitting plasma, but it could be coming from the accretion disk itself. But it could also be coming from the base of the radio jet. Okay, and what is clear here is that there is some magnetic fields are strong, first of all, they're present, they're strong, and you can see some kind of rotation as well. And the best or the most intriguing result that has come out from this work is that both these black holes, the emission that you see, can be explained by the BZ mechanism, the Blanford's-Naik mechanism. Even though one of them is an active galaxy and one of them is a quiescent galaxy. Sagittarius A star is right now not an active galaxy, right? We don't consider it an active galaxy. But the black holes in both of them seem to be driven. I mean, the mechanism for producing radio emission is the same. So that's quite interesting, and which also then kind of ties up with this idea. So this is an image of gamma rays from our own galaxy. So this is the galactic disk. Okay, so we are in this galactic disk. We are taking an image towards the galaxy center. And the galaxy center, there are these two bubbles, north-south. You can see that these are called Fermi bubbles. And the extent of these bubbles is a few kiloparsecs already. So one way to explain this is that at some point, the Milky Way was actually active and produced some jets and created these bubbles. So this kind of tells you already that even the so-called a quiescent galaxy could have passed through a phase of activity. And we know that all massive galaxies have supermassive black holes in them. And maybe at different times they get active. Okay, so this is what that is telling you. Okay, so now let's we'll try to now wind up everything with these, with this slide, which is quite interesting in the sense that what is showing here is the mass of the black hole and what is called a sigma, which is the stellar velocity dispersion. Okay, so let's just start from the beginning. So Ferraris and Merritt, these astronomers in 2000, and also Gebhardt et al., found that there was some kind of a tight correlation. So at that time, by 2000, there was already enough galaxies for which black hole masses had been found. So one way to actually find the mass of the black hole is, for example, what has been done in the Milky Way. So Milky Way astronomers have been actually monitoring stars around the black hole. So you actually have stellar motion. So the 25 years of data, which is why these astronomers got the Nobel Prize in 2020, was that they were actually monitoring stellar motion around the supermassive black hole in our own galaxy. And so once you actually have an orbit, you have the radius of the orbit, you know how fast the stars are moving, you can find the mass of the black hole, right? It's just mass is equal to v square r by g. So one way to do it is when you can actually see that we can only do in our own galaxy. In other galaxies, you can see how gas moves in the nuclear regions. So you again look at spectra and from the nuclear regions, and you can find out if gas is redshifted, blue shifted. From that, from the velocities of the gas motion, you can get the mass of the black hole. So in 2000, there were enough, a handful of galaxies when this had been done. So there were accurate black hole masses for those galaxies. And what these astronomers found was that there was a tight correlation between the black hole mass and the stellar velocity dispersion. So stellar velocity dispersion is basically kind of a measure of the spread in velocities of the stars in the galaxy. So this was very curious, right? Like why should the black hole or the stars in the galaxy know about each other? Okay, and so that was a curiosity, and that is why this concept of AGN feedback, it's still in inverted commas for a reason, came about, which I'll tell you a little bit. But this particular figure is actually from a later publication, 13 years later, where now by 2013 there were many more galaxies which had black hole masses. Okay, the techniques got better, we were able to get black hole masses. So now you see how tight it is. The initial thing was just like a few galaxies, but now it's like super tight. And all these different colors are different types of galaxies. So there is a tight correlation. So the idea is somehow the black hole knows about the stars and the stars know about the black hole. And what could be that link? So the suggestion is that link are those jets. That you have something which is being ejected from the black hole, which then maybe disturbs the stars. It could be either shocking the gas in the galaxy, compressing gas clouds. When they get compressed and they cool down, then star formation happens. So you are really, the black hole is kind of influencing the evolution of the galaxy itself. Even though it's even though it's very massive, its sphere of influence is very small, but because of these outflows, it can actually influence the galaxy evolution. So this was a very, very interesting result. And this particular relation is called the M sigma relation. So in fact, this relation is so robust, at least in the nearby universe, that if you have one of these values, you can estimate the other. So a lot of times this best fit slope is in fact used if you have just the spectra of a galaxy, and if you are able to get this, you can use the best fit line to get the black hole mass. So actually many of the galaxies have black hole masses through this M sigma relation. Okay. But then JWST came about, and it's also changed things dramatically. So what JWST has found, because it's operating in the near-infrared, mid-infrared regime, it's actually able to go very far, very early times of the universe, basically, very, very high redshifts. So JWST has found many, many things, but one very intriguing class of objects that JWST has found are called little red dots, LRDs for short. And so what these little red dots are, so these are the galaxies which are shown here. They look very red, they look very compact. You don't see anything, they look like almost just point sources. And you see the redshifts of these objects. 4.75, 8.92, 7.4 red. So JWST found these galaxies all the way between redshift 4 and 10. Okay, so now this is already again very, very close to the birth of the universe. But these black holes don't behave like the normal black holes that we see in our, in the low redshift universe, and actually don't seem to follow the M sigma relation. So the black holes in these, they are compact, of course, you can see, they show broad lines, like you saw in C4 galaxies in the first few slides. They show lines exactly like that, which was like the defining characteristic of a accreting supermassive black hole. They show lines. They don't show much X-ray emission. And the masses of black holes that you estimate from the lines, let's say from the Doppler widths and everything, the masses turn out to be much more massive than the galaxy mass itself. So these are more massive black holes in less massive galaxies. So that relation which we knew of in the local universe is not actually. They're much more massive than for their type of galaxies than anywhere else in the nearby universe. So that is peculiar. Okay, so this was one of the mystery which is not being solved actually. It's not. It's everybody. I mean, if you look at the AstroPH, every day, almost every day, there's a paper trying to describe little red dots. So this, actually, before I forget, I wrote this as discovery of little red dots because to kind of draw the analogy to the discovery of quasars. So a lot of astronomers think that this is as momentous as the discovery of quasars, the discovery of little red dots. Okay, so now I come to the last part of the AGN talk, which is where GMRT comes in. So this is the discovery of a very, very large radio galaxy, which was only detectable at very low radio frequencies. Okay, so here, this is an image. I don't know if you can see it actually. Maybe you can see it. You can see it, right? All the way to the end. So this is the extent of the galaxy from here till the end of that point, and that extent is 7 megaparsec. So we talked about Hercules A, which was 500 kiloparsecs. Now we're talking about a radio galaxy which is 7 megaparsecs. So these little things are some kind of hotspots, but inner hotspots, and they keep on going. So this is the LOFAR telescope image. The frequency of observation is 144 megahertz. And on the right, you have the GMRT image of the same source. And you see GMRT has better resolution than LOFAR. This is 650 megahertz. So you can see actually here now you can see jets connecting these different blobs in the outflow. So and then the insets are also telling you something. That is the VLBI image of this galaxy, and that is the optical image of the galaxy. So you see that red little thing is actually the host galaxy of that black hole. It's tiny. The galaxy itself is tiny, but the jet is 7 megaparsec in extent. This is a big challenge because if you think that the jets were actually generated by the BZ mechanism, where you saw these twisted field lines, right? When you have this kind of a magnetically dominated jet, then you should have a lot of instabilities that happen because of this. It's like, what is the analogy people use is that when you have, let's say, a telephone cord which is already wound up, if you keep winding it up more, it breaks up into more curls like that, and so basically that's a way for the jet to kind of lose stability. But somehow these jets have not lost that, and they continue to go to 7 megaparsec extents. So that is a mystery. And so I'll leave you with this slide, which is actually, of course, this is just a artist impression of this particular galaxy, and this was kind of release for, it was the press release for this result, associated press release. And what is now seen here, and this is actually what these authors also found, now you're seeing the cosmic web, so the large scale structure of the universe, and these are cosmic filaments which are basically galaxies and clusters of galaxies, and that black region here is the cosmic void, and this particular galaxy, the 7 megaparsec long galaxy, is actually inhabiting one of the filaments. And these authors got this information from actual, images of the SDSS, Sloan Digital Sky Survey, and so they know where it is in the universe. And this jet is kind of traversing 70% of the diameter of the void. Because it's so large, it's able to actually transfer particles and fields all the way from here till the cosmic void. So that makes it very super interesting again. So it's kind of populating the cosmic void with particles and magnetic fields. So this black hole is now, I told you the black hole seems to be affecting the stars in the galaxy and influencing galaxy evolution. Now it is going on much larger scales and influencing the universe, the large scale structure. Okay, so that is where I'll stop here, and then because I never gave anybody a chance to ask questions, I think we can have questions now.
Has there been any evidence of jets from black holes which aren't supermassive?
Of course. Yeah, so there are something called X-ray binaries, which are also microquasars. They are stellar mass black holes, which are accreting through a binary stellar companion, and they have accretion disk. They have jets as well. So there are microquasars. Then there are protostellar jets. Stars when young stars. When you must have seen those images of not just JWST but also Webb Space Telescope images of the, what is that region called? The great pillars, and the top you have,
The pillars of creation.
The pillars of creation, and the top of those you see jets, small jets. Have you seen those? Those are from stars. So you can, any kind of compact object can give you some jet, but the exact mechanism of the jet production may be slightly different between supermassive black holes and stellar mass black holes and stars.
So, what is your opinion of the answers on those interventions?
What is my thing? I don't really know. No, I have not been following so much either. So far we are actually just excited by all the things that's kind of all our understanding which is being defied by these, but I don't know actually. I don't know. Yeah.
Now can you explain the previous slide once again?
So what exactly? Like what is it?
I mean, these two images are referring to the same galaxy.
Yes, but they are different frequencies and different telescopes. So this is image at 144 megahertz with the LOFA telescope, the low frequency array, which is in the Netherlands, and the same image, the same source with the GMRT at 650 megahertz. Yeah.
So when you were explaining the mechanism behind that, there were two people who thought that when jet is being ejected, so one model was it extracts energy from the accretion disk and one was from the plasma.
Yes.
So you said that they thought about it. So is there any reasoning about the word? Like, is it not a found result or?
No, you're talking about the BPPC mechanisms. So what is the question about that?
So you were using the word that they thought that energy could be extracted.
Okay. So the thing was that this the existence of these very large jets, and which stay collimated to 100 kiloparsec scales, BZ mechanism was a theoretical way to try to explain their formation and their existence rather. But the so-called radio quiet jets or quiescent jets in the Milky Way, they don't have jets. And if they have jets, they're very tiny. So we never use the BZ mechanism for anything over here. In fact, a lot of times, if you look at the Seyfert galaxy I had shown you previously, people didn't even think that there were jets at all. So this emission here, this little thing that's coming out, it was not even suggested to be a collimated outflow. So BZ mechanism was not, used for explaining any of this. In fact, people suggested maybe the BP mechanism, which is the energy being extracted from the spinning accretion disk rather than the black hole, could give some less collimated outflows. So that was the expectation. But it looks like all black holes seem to be working with the BC mechanism. So that is very intriguing. Even though it was not expected, and especially galaxies which are quiescent actually, which are not even producing large jets, seem to be working the same way. So that is very interesting, because it also has also some link to the accretion rates. So I told you, right, the accretion rate decides the accretion structure. So if you have very low accretion rates, then the accretion disk is not a very thin disk anymore, but it actually puffs up, and it's called radiatively inefficient accretion flow, or RIAF. These are just jargon. But these kind of things were used to explain how you would get large jets, because when you have puffed up disks, they actually help in collimating jets. But both the Milky Way and IISER have very similar structures, very similar disks as well. So that was very intriguing. So why do we not have jets, for example, in the Milky Way? We should have a jet. That is the mystery.
So has it been observed that these jets diverge, or is that there's a physical jet angle which is making them collimated for like infinite times?
Say that again.
So like as you said that we haven't been able to prove over the large jets existing.
Yes.
So when we are saying that this mechanism has been being collimated, so does this keep acting for till when we observe, or do they diverge it?
Yeah, that's an excellent point. So I think the BZBP is still for how it is launched initially, and there's an extent to which it is kind of, you kind of explain, especially with using simulations, etc., only a certain distance. But somehow they seem to be collimated all the way. So it looks like the jets which are collimated initially stay collimated. That's what we see. And jets which are already having a little bit of an opening angle, they kind of open up. So that is observed. So yeah, I don't know if that answers the question. Maybe a little bit.
Ma'am, what exactly is the significance of these charged particles and magnetic fields being like fired into the cosmic voids? Like, how is that changing the structure of the universe?
That's a good question. So I think the expectation was that they wouldn't do anything to the cosmic void, and I mean, because first of all, actually I should tell you this, that even theoretically there was a suggestion that these the largest jets that could be present given this BZ mechanism, etc., or collimated jets through magnetic fields, was just a few megaparsecs. That was even theoretically predicted, but observationally it was found that these are much larger than that. Okay, so that's the first thing. The moment you have very, very large jets, the impacts are larger. That was also not expected. That it's kind of able to go to cover the entire cosmic void. And the fact of the presence of this jet, and that what we know is that these jets actually transport material from around the black holes till the end of the jets, is telling you that matter is actually being thrown out from this center of this galaxy to the cosmic void. So cosmic voids are not empty. So that all those implications, they come after the fact. This was the observation that was found, and so our understanding of cosmic voids also changes, right? And what it will actually do, I don't know what it's actually doing. So, but the picture that we have of cosmic voids being empty is not true. Yeah, that's a good thing. Yeah.
What I have basically read about black holes is it's a very high density matter.
Yeah.
From where even light cannot escape. So if we treat light as electromagnetic waves, so electromagnetic waves, then even magnetic field is not supposed to escape. So how are these jets being emitted?
Yeah.
And also you said about a relation between black hole and star. So what is the relation? Is there an interaction or some force or what?
Yeah. Okay. So the magnetic fields that we are talking about, and also the cartoons that we showed, this is still, it's the ergosphere of a black hole. This is not exactly the event horizon. It's a little further, beyond. That place you can actually kind of anchor magnetic fields. So that way it's not kind of violating any of our understanding of what black holes are. Magnetic fields can exist around a certain after a certain distance from the event horizon. that close relation between black holes and stars. So I already showed you, for example, even this. Okay, this is not a great example, but let's say you have the black hole in the center, and then there is this jet. The galaxy is here. When this jet is kind of moving through the galaxy, it could be either throwing the ISM around, it could be compressing ISM, it could be shocking ISM, it could do many, many things to the ISM. And those many things then translate either into increased star formation, decreased star formation, those kind of effects. So then that is how your black hole, through these outflows, is kind of controlling the evolution of the galaxy itself. That is the whole process is called agent feedback. And even now, I mean, there is still a lot of debate going on whether this actually happens. I mean, sometimes you see actual signatures. You can see maybe the jet is actually going, and then you can see maybe some star formation at the edge of the jet in some cases. But it's not always seen. So that question, I mean, there is a suggestion that could explain the M-sigma relation. But exactly what is happening is still not 100% clear.
You mentioned something called equipartition magnetic field. What is it? Can you?
Yeah, sure. So equipartition magnetic field, see, we because of this plasma which is emitting synchrotron radiation, and synchrotron radiation has like a power law slope. So if you just actually plotted flux density versus frequency, it has a particular slope which is called the spectral index. But you don't see anything apart. You don't see, for example, emission lines from this plasma. Because if you saw emission lines, then you would know what the plasma is made of. But we don't see anything, you just see this power law. So there is no way, because you know how you get magnetic field strengths. For example, if you have some gaseous or gas, which is showing emission lines, you can do some Zeeman splitting experiments. You can do things and try to get magnetic field strengths. But there is no way for us to get magnetic field strengths for these plasma, synchrotron emitting plasma, because of this power law thing. So we do the next best thing, which we assume that there is some kind of an equipartition of energy between the charged particles and the magnetic fields. So you assume that the charged particles which are emitting the synchrotron radiation and the energy of magnetic fields is equal, and then from that synchrotron emission you can kind of estimate the magnetic field. So that is called the equipartition magnetic field. So it's like an assumption. There are many assumptions that go into that calculation, but that's the best we can do. And these B fields that turn out to be very, very small actually, like micro Gauss kind of fields.
Are there any more questions? So I think we'll conclude for today.
Thank you.
Thank you, ma'am.